Swayam Prabha. Digital India. Educated India.
Hello and welcome everyone to this course on gas turbines and jet engines. So, today is lecture 13 of this course and we are going to study in today's class intercooling plus reheating combined together in a gas turbine cycle or a combined intercooled reheat gas turbine cycle. Okay. So, the concepts that will be covered in this course, we will of course analyze the combined intercooled and reheat cycle, and in addition to that we will also solve a numerical problem based on the same design parameter values as we had taken for previous problems, and we will solve this problem for the intercooled reheat cycle and compare the efficiency and work output which we obtain, the performance parameters, with all the previous cases to get a quantitative idea about how the values change for this type of cycle. Okay. So, what is intercooling with reheating? So, as the name itself suggests, we now have both intercooling as well as reheating. Okay. So, I will start with a simple TS diagram. So, we now have both intercooling and we will assume that both are operating at optimum or has been designed to operate at optimum conditions, both the intercooler as well as the reheater. So, I will explain each of this process in a minute. Let us draw this part again. Okay. Let us see what are the processes involved. So, for the intercooling part, it is similar to intercooled cycle. So, from going from 1 to 2 is the low pressure compression, 2 to 3 is the intercooling, okay, or the heat removal at constant pressure. So, this is a constant pressure process. 3 to 4 is the high pressure compression, okay, taking it to the highest pressure in the cycle, which is the pressure for the primary combustion. So, this 4 to 5 is the primary conversion, okay, this is where the heat addition occurs. Then we have 5 to 6, which is the expansion in the first turbine. Remember that when we have reheating, we have two different turbine processes. So, this first part is known as high pressure turbine, because here the expansion occurs from very high pressure to the maximum pressure to the reheat pressure. So, higher pressure as compared to the second turbine. Then heat addition using secondary combustion. So, this is what we had called as reheating. Okay, we are again heating back the combustion products to the maximum possible temperature, which is the turbine inlet temperature, okay, or design turbine inlet temperature, and then from 7 to 8 is the expansion in the low pressure turbine. So, the exhaust will occur at state 8, but in ideal cycles we close out the theoretical cycle by adding a hypothetical heat removal process which occurs at constant pressure from 8 to 1. Okay. So, this is our cycle, and you can see that now we have two compressions and 2 expansion processes, and the combustion also. So, we have now 2 times because of reheating, and in between we have the intercooling also in between the compression processes. Okay. So, we know that for optimum conditions, we will study for optimum conditions. So, optimum conditions T2 equal to T4. In general, we also know that T3 should be equal to T1, which is the ambient equal to the ambient temperature, and T5 and T7 are equal to the turbine inlet temperature. So, T5 is equal to T7 equal to the maximum temperature that is possible in the cycle. Okay. Now, what else is known? We also know that the pressure ratios are constant across the intercooler. So, pressure ratio across the intercooler P2 by P1 is equal to P4 by P3 is equal to root of R, okay, root of the overall pressure ratio. This we already know. Similarly, for the reheater P5 by P6 is same as P7 by P8, and this is also equal to root of R because this is equally split. So, we see that all the 4 pressure ratios are same, okay. All the 4 pressure ratios are same, which means that this pressure at 2 is same as the pressure at 0.6. Okay. So, pressures at 1 and 8 are same. So, let us say that if they are 1 atmospheric pressure, that will be the case. At 4 and 5 are same. So, if it is 10 atmospheric pressure, we will have 10 atmospheric pressure at 4 and 5, and pressure at 3, 2, 6 and 7 are all equal, when should be equal to root of R. Okay. So, root of 10 in that case, whatever is the value 3.2 something. Okay. So, all the pressures are equal for this optimum condition directly, which we can see. So, now if we want to derive the expression for the efficiency and net specific work output, the work output of course changes as compared to previous cases, because in this case we have 2 expansion processes and 2 work addition, means work needs to be provided to the compressors. So, we will have Cp into T7 minus T8 from the low pressure turbine plus work output from the high pressure turbine Cp T5 minus T6 minus work input to the low pressure compression Cp T2 minus T1 minus work input to the high pressure compression Cp T4 minus T3. Okay. Because T7 minus T8 is equal to T5 minus T6. Remember, T7 is equal to T5 and T8 equal to T6, which we have established just a few minutes back. So, we can write this as Cp T7 minus T8 into 2, okay, 2 times of Cp T7 minus T8, and because T2 is equal to T4 and T1 is equal to T3. So, these 2 terms are also equal. So, we can write this as minus 2 Cp T2 minus T1. Okay. So, this now in non-dimensional form we can express this. Let us go to the next slide. So, in non-dimensional form, W net by Cp T1, this is equal to, let us go back and see what was the value, 2 Cp T7 minus T8 plus, not plus, minus 2 Cp T2 minus T1. divided by Cp T1. Cp will get cancelled and we are left with T7 by T1. What is T7 by T1? It is equal to temperature ratio T. Okay. So, T7 by T1, maximum temperature to inlet temperature, so or minimum temperature. So, this is equal to T. So, 2 T minus what is T8 by T1? T8 by T1 we can write as T7 by T1 into T8 by T7. Okay. T8 by T1 is equal to T7 by T1 into T8 by T7. So, T7 by T1 we have already established that this is equal to T. T8 by T7. So, T8 by T7. So, T7 by T8 is 1 by or T7 by T8 is root r to the power gamma minus 1 by gamma, okay, which means that this is equal to root c. So, T8 by T7 is 1 by root c. Okay. So, this will be T multiplied by 1 by root c. Okay. So, T minus T by root c minus 2 T2 by T1. T2 by T1 is equal to root c, okay, again. So, root c and plus T1 by T1 is 1. Okay. We are keeping in terms of minus outside. So, here we will keep the minus sign because we are using a bracket. So, minus 2 c minus 2 root c minus 1. Okay. So, this is the net work output. Again remember that these are not formula, these are now we can plot the net work output for different values of C for a given value of T, and we will obtain the performance characteristic for net work output for this cycle for different values of C, and we can repeat the process taking another value of T, then again another value of T, and we will get the entire performance map for this case. Otherwise, directly it is not easy to say how the variation will look like unless we plot the values. Okay. So, the efficiency then in this case will be equal to Cp T1 into W net. Okay. So, Cp T1 into this non-dimensional value. So, which is equal to 2 T minus T by root c minus 2 within bracket root c minus 1 divided by Q in. What is Q in? So, now we have two heat addition processes, the primary combustion and the secondary combustion, similar to normal reheat cycle. So, this is Cp T5 minus T4 by plus Cp T7 minus T6, Cp T5 minus T4 plus Cp T7 minus T6. Okay. Cp T5 minus T4 plus Cp T7 minus T6. So, now if we take T1 out from the denominator and cancel the Cp T1, we are left with 2 T minus T by root c minus 2 root c minus 1, and in the denominator we have T5 by T1. Again remember that maximum temperature by the inlet temperature, minimum temperature. So, this is equal to T. T4 by T1, what is T4 by T1? T4 by T1 is equal to T4 by T3. So, that is equal to root c minus root c. then T7 by T1, T7 by T1 is again T. Okay. So, again T. So, I will write 2 T minus T6 by T1. What is T6 by T1? T6 by T1 is equal to T8 by T1, because T6 and T8 are equal, and we have found that T8 by T1 is equal to T by root C, okay, minus T by root C. Okay. This is the expression for the efficiency of this intercool plus reheat cycle in terms of the temperature ratio T and the pressure ratio, which is written in terms of C here, where C is equal to pressure ratio R to the power gamma minus 1 by gamma. It is a complicated expression. So, directly it is difficult to visualize how the variation will happen, but we can plot this and try to find out the variation graphically. We will do it in the subsequent classes. Okay. So, now let us see how the qualitatively how the performance parameters will look like. Again I will say that directly from this plot it is, or from this expression it is not easy to say how these performance parameters will vary, but once we plot it using numerical tools we can see how it varies, and that is that variation I am qualitatively going to show here. Okay. So, this is not needed. So, performance characteristics. So, let us say that this is efficiency versus R, and this is net specific work output in non-dimensional form versus R. Okay. We have the standard values at R equal to 1, we have the theoretically minimum value. This is also at R equal to 1. So, the standard Brayton cycle, by this time we are very familiar with this, keeps on increasing monotonically. Then for reheat cycle we had seen that. So, pure reheat cycle we had seen that the variation is something like this. So, it is lower for all cases, lower compared to the standard cycle, but keeps on increasing with increasing value of T, although it never reaches the standard Brayton cycle efficiency. So, this we had drawn for T equal to 3. I am drawing for discrete values, but for any other value also it could have been drawn. So, I am drawing for some rounded values T3, T4, T5, but for any other values also this could have been drawn. Okay. So, now this is for reheat. So, when we add or only for if there is only intercooling, then we know that the efficiencies will be slightly higher compared to reheating. Okay. Let us draw for one or two cases, only intercooling. Efficiencies are going to be higher slightly. I am drawing two lines only, because otherwise it will get too congested. So, T equal to 5 and T equal to 4. This is for only intercooling. When we combine these two, then we get the lowest efficiency, sort of expected, because both the processes reduce the efficiency, and our purpose of adding reheat and intercooling together is not to improve the efficiency, but to improve the net specific work output. Okay. So, typically because we get very less efficiency here, generally these are not used just together standalone, but regeneration is also added to this, as we will see in the next class, and that makes it a very powerful combination. Okay. So, this will be something similar to, let us say, T equal to 3. slightly lower. I am drawing it to be to show a larger gap, but actually it will be slightly lower than the reheat cycle, and similarly you have T 5. Okay. All are slightly lower as compared to the corresponding reheat and intercool cycle, but the nature of variation is same for all three cases, because the efficiency increases with R and efficiency also increases with T. Okay. So, efficiency is increasing with R, which is very different from those of the regenerative cycles. Okay. Intercooling, intercool plus reheat. Quantitative comparison we will see after 2 classes. Okay. We will compare all the cases by plotting numerical values and see how the actual quantitative differences are. So, the work output, standard Brayton cycle work output we already know. Okay. Let us draw for only one case. Okay. We can draw for other cases, becoming very congested. R equal to 5. So, this is standard Brayton. We know that reheating increases the work output significantly. So, same R equal to 5 reheat. Intercooling is somewhere in between. Okay. So, it has positive effect, but not as strong as reheating. But combining intercooling and reheating leads to very high efficiency, okay, very high efficiency, because now we get the advantage of both reheating and intercooling on work, like the increase of work output. So, R equal to 5, this is intercooling plus reheating. So, you get the highest efficiency. Okay. All are drawn for the same value of not R. So, I have wrongly written R here. All are for the same value of T. Of course, we are plotting the variation with respect to R, but all are for the same value of T. So, T equal to 5, this is also T equal to 5, T equal to 5 and T equal to 5. Similarly, we can draw for other temperature ratios like T equal to 4 or T equal to 3 or T equal to 2. We will get similar variations, like the nature will be same and the relative increase or decrease will remain similar, but the overall values will be lower for lower temperature ratios. Okay. So, by intercooling and reheating we get the highest work output, but the efficiency decreases because of twofold reason. One is that we are adding significant amount of heat in the secondary combustion, plus we also have to use up more of the turbine work output for running the we have to add more heat after the intercooling process. The combustion process needs higher heat addition. Okay. So, by combining these two factors we need significantly high heat addition to the cycle. So, the efficiency is affected negatively, but the work output increases. Okay. So, before finishing the class, let us take a quick look at a numerical problem. Okay. So, before going into the numerical problem, I thought that it would be better if for reference we take up a problem previously solved, which was for pure reheat cycle, and now we will see the difference when we had intercooling to it, okay, because that is the closest comparison. So, intercooling plus reheat has more extreme behavior as compared to pure reheat cycle, which had the most extreme behavior previously till now. Okay. So, let us see whether we get that. So, previous problem for reheat we had obtained for the same temperature and pressure that we are taking for all problems, 300 Kelvin and 1 atmospheric pressure, pressure ratio of 10 and T max of 1500 Kelvin. We had obtained the efficiency as 41.9% and the work output as 564.54 kilojoule per kg. Heat input was very high, 1347.96 kilojoule per kg. We will see in our case how this compare. Okay. So, let us take the example and let us start by solving by drawing the TS diagram to solve the problem. So, we are running out of time. So, we will solve the problem quickly, but luckily for us most of the values are already derived in the previous problems. So, become a very narrow cycle. So, this is 1 to 2 low pressure compression, 2 to 3 intercooling, 3 to 4 high pressure compression, 4 to 5 primary combustion, 5 to 6 low pressure high pressure expansion, 6 to 7 secondary combustion or reheating, 7 to 8 is the low pressure expansion and 8 to 1 is the hypothetical heat removal process at constant pressure. And what conditions are given? Ambient temperature is given. So, T 1 should be equal to that ambient temperature 300 Kelvin. Pressure we will not need. If you need, you can note it down as 1 atmospheric pressure. Then the pressure ratio for the overall cycle is 10 and what else? The maximum temperature T max, here it will be T 5 and T 7. So, this is 1500 Kelvin. So, these are our design parameters. Apart from this, we also know what are the conditions which are satisfied for optimum reheating and intercooling, optimum intercooling and reheating. Which are the conditions? So, T 7 or T 6 equal to T 8 optimum reheating and T 4 equal to T 2 for optimum intercooling. Apart from this, we also know that T 5 is equal to T 7 and T 3 is equal to T 1. Okay. We want to find out the efficiency and the net specific work output, like for all the cases. Problem is defined in the same way, so that we can do a direct comparison, which is very helpful for our understanding. So, quickly we will go through this. So, T 1, okay, the values T 1 and T 3 are both equal, as we have already mentioned. So, this is equal to 300 Kelvin. What else is known? T 5 is equal to T 7 is equal to the maximum temperature or the turbine inlet temperature, which is 1500 Kelvin. Then T 4 is equal to T 2. Okay. So, for intercooled cycle, we know that T 2 by T 1 is equal to root of R for optimum condition, root of R to the power gamma minus 1 by gamma. So, if you solve this from here, you will get a value of T 2 equal to 416.85 Kelvin. You can compare this to the simple intercooled cycle, you will see that this is the same value. So, T 4 is also equal to that 416.85. Okay. And we know that T c is equal to T 8, T 6 equal to T 8, and what is the value of T 6? So, again T 6 and T 8, this will be exactly same as the reheat problem. Okay. So, T 6 by T 5, let us say, is equal to 1 by root R to the power gamma minus 1 by gamma, okay, from this process 5 to 6. So, this gives us a value which will be same value as the reheat problem. In reheat problem we had this value here as 1079.53 Kelvin. Okay. So, here also you will get, you can solve and you will get 1079.53 Kelvin. So, now the temperature at all the states, all the 8 states are known. So, we can find any of the required variable values. So, we can directly find the W net value. Okay, W net is 2 into C p T 5 minus T 6. Why 2 into C p T 5 minus T 6? Because T 5 minus T 6 is equal to T 7 minus T 8 minus 2 into C p T 2 minus T 1. Again, because T 4 minus T 3 is equal to T 2 minus T 1, we are writing this as 2 C p T 2 minus T 1. Okay. Replace the values and you will get a work output value of 610.28 kilojoule per kg. How does it compare with the reheat cycle? Reheat cycle we had very high value 564.54, now it is even higher. Okay. Actually, among all the cycles, this cycle gives the, along with the next cycle that we will study, gives the highest work output that is possible from these theoretical cycles. Okay. What about the efficiency? For this we need the heat addition. So, heat addition is equal to C p T 5 minus T 4, which I already know, we already know the values, plus C p T 7 minus T 8. Okay. So, this comes out to be equal to 1511.14 kilojoule per kg. How does this compare to the reheat cycle? Reheat cycle we had very high heat addition or heat requirement 1347.96 kilojoule per kg, but here it is even higher. Okay. So, it is the highest amount of heat which is needed among all the cycles for the given parameters. Okay. Finally, we get the efficiency as W net by Q in, that is equal to 0.404. Okay. So, efficiency is lower than even the reheat cycle. Okay. So, if we compare this, we have, so we have in tabular form all the values. Standard cycle we have the lowest amount of work output 446.08, efficiency is intermediate for 48.2%. Now, adding reheat we know that work output has been increased to 564.54 and adding intercooling had increased the work output from standard cycle to some intermediate value of 491.83. Now, adding intercooling plus reheating increases the work output to the highest value, as you can see 610.28 kilojoule per kg. So, this trend will remain same even if you use other design parameter values, other values of R and T. Similarly, the efficiency while adding reheat was considerably reduced to 41.9%. Intercooling also had a negative effect, but not as drastic as reheating, but combining both of these give us the lowest efficiency among all the cycles possible. So, we get the lowest efficiency which is 40.4%. So, from efficiency point of view this cycle is not suitable, but this gives us the maximum specific work output. So, we will need the minimum amount of working fluid for a given power requirement. Now, if we combine this with regeneration, then it becomes a very powerful cycle, because the efficiency there significantly improves and the work output remains high, and that is what we are going to study in the next class, okay, which is the final type of cycle that we will study for this ideal cases, and then we will go to more practical gas turbines or gas turbine analysis. So, we conclude this by summarizing what we have learned today. We have analyzed Brayton cycle with combined intercooling and reheating, learn the performance characteristics of this cycle and how they compare with similar other cycles, and solved a combined intercooling reheating problem and compare the obtained performance values efficiency and net work output with those of the other cases, okay, and seen that the efficiency is the lowest, but the work output is the highest among all the cases discussed till now. So, with this so these are the references for background study. With this we end today's class, and will continue the final cycle in the next class. Thank you, and we will meet again in the next class.